Today we have, Weinan Lin speaking on the May Spectral Sequence.
Wait a minute. Continue. Okay. Hi everyone. I'm Weinan Lin. I'm from the University of Chicago. I'm working with Peter May, and so today I'll be talking about the May Spectral Sequence. So we know that to compute the stable homotopy graph spheres, I put stable here. So this is the stable homotopy graph spheres, and we have the Adams spectral sequence, which starts from the cohomology of the Stingrod algebra over prime 2, and so it's the X group. And so the left-hand side is totally algebraic, but it's hard to compute. And I think so far we only have like the edu page up to maybe 200 stem by some. I think it's not public, but someone has done that. But basically, it's very hard. So in May's thesis, he used another spectral sequence to compute the E2 page of Adams, which is the May spectral sequence. It starts from the cohomology of the associated gradient algebra of the Stingrod algebra, and it converges to the E2 page of Adams. Okay, and so the E2 page of Adams, it has two gradients, but because of the filtration, we have 3 gradients on in the May spectral sequence. And here for I use the total grading for the first two grading, and this U grading is from the filtration. So first I want to talk about how to compute the E2 page of Adams. So the E2 page of Adams is isomorphic to the cohomology of the Kobar complex. So usually one of the classical way to do it is that you can use the bar complex of A, and then because it's X, you have to dualize that to get the X group. But since A is a Hopf algebra, you can dualize the bar complex before you take the homology. So if you dual the bar complex, you get the Kobar complex written using the elements of the dual Stingrod algebra. Okay, the Kobar complex is basically the tensor algebra of the augmentation ideal of the dual Stingrod algebra. So I use J for the augmentation ideal for the dual Stingrod algebra. I reserve I for the augmentation ideal for A itself. Okay, so now let's define. This is the differential of the Kobar complex. So that lives in a cohomology degree S. So we have A1 tensor until AS, and the differential is given by this. So you break AI into 2 tensor summands, which are the summands of the diagonal coproduct of AI. And so here, because I'm considering the augmentation ideal, so I ignore the 2 trivial terms. So AI prime tensor AI double prime is the non-trivial part of the coproduct of AI. Okay, but usually people will not use this Kobar complex to compute that, because we all know that the Kobar complex is huge, so it's just hard to work with. So we have to find some way to compute that. And the idea of May is that we can filter A again. And here we filter A by length. What it means that we consider the powers of the augmentation idea of A. So here I is the augmentation idea of A. And we look at how many times an element in A can be decomposed into products. So here FPA is all the P products of A. And so it's a decreasing filtration. So the associated gradient algebra of the Stigner algebra is sorry, I forgot the direct sum here. It's all those FPA over FP plus A for all P. And the filtration of A induces a filtration of the dual Stigner algebra, and hence a filtration of the Kobar complex. So once we have a filtration, we obtain the spectral sequence. And that spectral sequence is the May spectral sequence. And so we filter this DGA, and now we get the spectral sequence. The E2 page is proved to be the cohomology of the associated gradient algebra, which is defined here.
Does this work for any Hopf algebra?
Yes, yeah, I should mention that. So the title of May's thesis is the cohomology of Lie algebra, Lie algebras and application on Stigner algebra. So basically, in May's thesis, everything are quite general. That's why you all also have a lot of May type spectral sequence in many other contexts. For example, like this Friday, the Liam talks on May spectral sequence for THH. So basically, this works for all Hopf algebra A. I mean, any some Hopf algebra of some finite type. Like for example, if in every degree it's finite dimensional, then that's fine. So for suitable Hopf algebra, for very large variety of algebras and filtrations, this works. So basically, it's the same. You filter A by powers of the augmentation ideal, and that's it. And with those suitable conditions, you can make sure that the spectral sequence converges to all we want. Okay, so but today I focus on the Stigner algebra, though you have to know that this approach actually works for a lot of Stigner algebra. For example, like I think Novikov, the Adams-Novikov spectral series is also kind of like the May type spectral sequence. Okay, so the good things about this is totally algebraic. I mean, this is totally algebraic, and that is also algebraic. The whole thing is algebraic. Now let's talk about the E2 page of the May spectral sequence. So the E2 page of May can be computed by the cohomology of the Kobar complex. So remember that the E2 page of atoms is computed by the Kobar complex, which is the Kobar complex of the dual Stigner algebra. But now I replace that with the associated gradient algebra of the dual Stigner algebra. So if we compute that, we get the E2 page of May. And so what's the structure of the associated gradient algebra of the dual Stigner algebra? We know that the dual Stigner algebra, so thanks to Milnor, we know that the dual Stigner algebra is a polynomial algebra of Gauss, and but the associated gradient version is an exterior algebra of Rij. Here I'm using the May's original notation, and so Rij is the projection of Cj to the 2 to the I, and so now that the co-multiplication is given by this, it corresponds to the co-product on Kasai that we are familiar with. They look exactly the same if you know that Rij stands for Kasai j to the I. Okay, any questions so far? Okay, now now it's still a problem that it's again a cobalt complex. Though E naught A star is kind of easier than A star, the dual steric algebra, the cobalt complex is still kind of huge. And May has found a much smaller complex X, which is a homology isomorphic to the cobalt complex. So basically, the homology of X is the same as the homology of or the cohomology if you consider the degree of the differential of the cobalt complex of E naught A. And so now we consider X instead. X itself, it's a polynomial algebra. So it's the kind of our favorite algebra, I mean, no relations at all. And the differential is given by that. So note that it's almost the same as that. It's just that we get rid of the tensor product, and it's commutative. It's a polynomial algebra, and the gradient is given by this. That's S degree. The cohomology degree is 1. The topological degree is that, and that's the same thing as the degree in the sterile algebra. And U is the kind of the May degree. It's the lower index Z in Kasai Z. So the main goal of this talk is to compute the cohomology of this DGA. It looks kind of simple. X looks kind of simple. It's a polynomial algebra, but the computation of HX is actually very hard. And that's the E2 page of the May Spectral Sequence. Any questions? So I will let you stare at this for a moment. So it's polynomial algebra, which is, this is exactly given by correspond to the coproduct of the Kasai. Okay. Now I have some tricks to remember this coproduct. This differential formula. And one helpful way to remember this is that we put these generators into a matrix that so 0, the upper index stands for the rows. So that's the 0th row, first row, second row, third row. And the low index stands for the diagonal lines. That's the first diagonal line, second diagonal line, and third diagonal lines. And now the differential can be written as dr equal r squared. So that's the matrix multiplication. So this is actually a matrix multiplication if you write those I, J this way. So actually it would be natural to re-index this. So, yeah, so in my paper, I prefer to index R this way, that I use the usual index we use for matrix. That's Rij is in R row in J's column. So that's how you define it. And now the differential becomes nice. It's exactly the matrix multiplication. Very easy to remember, right? If you compare to this, for this you might have to think for a second, but for that it's very easy. That the X is the polynomial algebra of upper of the interest of the upper triangular formal matrix, and the differential is given by dr equal r squared, and that's it. That's what X is. So now we have the DGA X polynomial algebra of interest in the upper triangular zone, strictly upper triangular, and differential is given by this. And here's the question: what's that? So the first question is, what's the indecomposables? Of course, it's almost impossible to imagine what the whole algebra is, but it makes sense to ask the first question: what are the generators of this algebra? And in May's thesis, he has given many examples. For example, Ri plus 1. So that's if we go to this, it's this element is the element in the first diagonal line, and because of this formula, you see that if j equals I plus 1, then because here, in order to get a non-trivial summand, k must be strictly between I and j. If I is right next to j, then there's no differential. The differential is trivial. So therefore, I plus 1 is a cycle, and the homology class is denoted by HI. And because we are working over prime 2 right now, I also have to mention that in May's thesis, he studied all primes. 2 is just one of them, but right now I'm focusing only on prime 2. So because we are working on over prime 2, all squares are cycles, because the x squared equals 2x, which is 0 over prime 2. So these are also cycles too. We denote them by Bij. So I have to warn you that the May and Ravenel in Tangora, they use 3 different sets of notations for this Rij, and I'm using a fourth notation which conflicts the Tangora's notation, but I like this because this is so simple, so easy to remember. It's just the matrix multiplication. So in my talk, I stick with my own notation. So, and also for Bij, May use B upper I lower j notation. I'm using the one that agrees with the align with the Rij. Okay, and now we have more examples of elements in the cohomology, like this one, and it's denoted by H0, 1. That's May's original notation, and actually all people use this. All people use the same notation for these elements, and so if you sit down and check, compute the differential of this, they are cycles, and it turns out that these are indecomposables in the cohomology. And in general, so May has defined a very large collection of these types of indecomposables. And here S is a sequence of number like 1 and 1, 3, 1, 2. And you may wonder what S looks like in general. And though I will not repeat May's original definition, but use the matrix trick, I can tell you quickly what these elements are. So for example, H0, 1 is the homology class of this chain, which is a determinant. So if you look at the matrix of the generators, it's this block, which is in the zeros row, first row, third column, second column, third column. And for H0, 1, 2, it's the homology class of this chain, this determinant, 0, 1, 2, and 3, 4, 5. And for H0, 1, 3, it's this. This one, it becomes, it's getting more interesting now that the number of rows is 0, 1, 3, and the columns are the second column, fourth column, fifth column, and there's a 0 here. And that explains why H013 has fewer surmises, because there's a 0 in the determinant, so it has fewer surmises. Okay, so I can tell you the pattern now that you see that the number of the columns and the numbers of these rows and columns, when you add them together, they form a consecutive numbers. I mean, 0, 1, 2, 3, 4, 5. And we always need that because we want the determinant to be a cycle. So if you always split two consecutive numbers into two sets, one for rows and the other one for columns, then that determinant would be a cycle if these numbers are consecutive. I mean, there's no gap between them. If there's no gap between them, okay. And you may wonder, what about the patterns for rows? What kinds of rows that you can find that indecomposable? And the pattern is this. In general, if you start with the expression of nested parentheses, for example, like this one, such that it should be a valid parentheses expression, and the leftmost parentheses should match with the rightmost parentheses. And here is our consecutive integers starting from I. Then if we consider the rows, I plus S1, I plus S2, I plus SK corresponding to these left parentheses. For example, this I and I plus 1 and I plus 3, and the rest numbers as columns. Then we can obtain an indecomposable, which we denote by HI S1, S2 until SK, which is the homology class of the determinant of the submatrix of R consisting of entries of these rows and columns. So consider the ith row, I plus first row, I plus third row, and I plus second column, I plus fourth column, I plus fifth column. Then that element is denoted by, in this case, denoted by HI1, 3. So that's this example. This is the rows 0, 0 plus 1, 0 plus 3, and that's why it's called H013. It's the homology of this submatrix. And in general, it's one-to-one correspondence. So you may wonder why we need a condition that that this should be a valid parentheses, nested parentheses expression, because we want the determinant to be non-zero. We want to make sure that the number of the columns should not be too small, because we have a lot of zeros here. If the indices of the columns are too small, then this matrix will end up with a lot of zeros in it. So eventually you vanish, you'll be a trivial determinant. So that's why we need that to be a valid parentheses expression. And the reason we want the leftmost parentheses to match with the rightmost parentheses, we want to make sure that it's indecomposable. For example, if we ignore the most left one and most right one, then we end up with the two parentheses expressions. So actually, you break into a product of this kind. You break into the product this one and that one. So this one is actually HI plus 1, and that one is HI plus 3. So, but if you make sure that the left one is matched with the rightmost one, then it's an indecomposable. It does not break into a product. Okay. Now here's the conjecture of in May's thesis, that he conjectured that this HIS I have to mention that when S is empty, when we have only one pair of parentheses, I mean I and I plus 2, oh sorry, I and I plus 1, then S is empty, so we simply omit S and write HI. So HI corresponds to the simplest expression, which is the matrix of one entry located in ith row and I plus 1, I plus first column. Okay, so that include HI is included in this. Okay, so these elements HIS and BIJ, they form an additive basis of the indecomposables of the E2 page of May. So May conjecture that they are all indecomposables. So he has actually proved that these are indecomposables. I mean, you have to prove this first. They are indeed indecomposables, and the way he proved this is that he considered the dual of X, and which is a coalgebra, and he computed the coproduct of the dual of this HIS, and it turns out that they are primitive. So if you dualize that, it means that they are indecomposables. Okay, but it's very hard to prove that they are all the indecomposables you need to generate HX, and that's kind of my goal to prove this. And I mean, you can see that X is kind of a small, I would call it a gorgeous DGA, it's a polynomial algebra. The differential is given by matrix multiplication, but it's hard to imagine that still we cannot figure out what the homology looks like, what the indecomposables look like. Although we conjecture, if you read May's thesis, of if you have done a little bit of this computation, you strongly believe that this conjecture is true. At least May has verified this conjecture up to stem 164, and stem is T minus S, where T and S are two of the gradients. Okay, and so now I'm going to tell you how I'm attacking this proof right now. So I'm using a certain kind of inductive method, but in order to prove this conjecture, I haven't finished the proof yet, but in order to do it, I have to use a little bit information about how these indecomposables relate to each other. I mean, what relations are. So, and in the end, I end up with a conjecture, a stronger conjecture that tells you what the whole E2 page is. And so I claim that, I conjecture that it's the E2 page of May is generated by this with 8 different kinds of relations. And here I'm kind of using a different notation because S stands for rows and T1 stands for columns. Usually it will be verbose because T1 is determined by S1 because they form 2 consecutive integers. But I exposed the columns here because I want to do some set manipulation. So T1 it's a set. These are sets of columns and rows. So I'm manipulating the sets of rows and columns, and that's how it works. That's so here I've omitted a lot of conditions here. They all have conditions on what J and ST should be, but in order to fit into the slides, I've omitted them. But the point is that the whole thing is kind of manageable. I mean, at least you can write all of them. So I've actually proved all these relations except the last one. The last one is a little bit tricky, but I've proved the rest by explicitly constructing chains such that the differential of the chains, the boundary of the chains is exactly the relation you want. It's a little bit painful, but in the end, it can be done. And I also have another conjecture that it's quite interesting that the E2 page of May, it turns out that, it doesn't turn out, we haven't verified that yet for the whole algebra, but at least for the lower degree computations, low stem computations, the algebra is nilpotent free. So I've actually done some computations that the conjectures are actually true in a smaller, in a sub DGA of X. So this homology, so X7 is actually a retract of X as a DGA. So the cohomology is a sub algebra of the cohomology of X. So here X7 is given by this. It's a sub polynomial. You focus the sub matrix of the whole infinite matrix, which is the 8, because we start with 0. It's the 8 by 8 matrix. So you consider that only, then this sub algebra of the E2 page of May, it turns out that this is nilpotent free. So I would consider 7 is already kind of big enough so that you believe that it's true in general, that that is nilpotent free. And it's a little bit curious because we all know that because by Nishida, we know that the homotopy group of spheres is nilpotent. I mean, except it's 0. So all elements in the stable homotopy group of spheres in positive degrees, they are all nilpotent. But if you go way back to the E2 page of May spectral sequence, and here it's nilpotent free. There's no nilpotent elements at all. And so in some sense, the May spectral sequence is killing this kind of regularity, certain kind of regularity that eventually elements are becoming more and more nilpotent. Okay, and I use the global basis to do this computation. I've determined the cohomology of X7 completely. I mean, for people who are curious, it kind of looks like it kind of looks like this. Remember that I've classified the relations into different types. So these are some of the relations. That this is the relations of type 1, and these are the relations of type 2. They are all kind of a product of 2 elements, and it becomes 0. And these are relations of the third type, and they all have a pattern that there's always a Bij in it, and that's 3b. And these are more tricky. That at least Peter May wasn't aware of these kind of patterns, but use the tricks of the matrix and determinant thing. I actually have a single formula to describe all these relations, and then that's the 5th type relations. These are kind of very long, and that's the last kind of relations. And these are actually the hardest one to prove. I haven't found a universal chain to prove these relations yet, but at least I know these are true. I mean, there are only finite many of them have computers. So basically, I know at least these relations holds up to some stem. And okay, and by the global basis, I can organize these relations by global basis. It turns out that I can find an additive basis for the whole algebra, such that the additive basis is square closed. So if a monomial in my additive basis, if a monomial is in my additive basis that I have chosen, then the square of that monomial, or all the powers of that monomials, are again in the basis. So you see that automatically that proves the algebra is nilpotent free, since you can always write elements in terms of the additive basis you choose. And then if the additive basis is already power square closed, then you square it, still it's a non-trivial summation and of additive basis. And so that's how I prove it. I just computed X7 completely. So originally in May's original paper, he has computed the e to the page of May up to, you see that it's relatively shorter compared to my computation. It computed, computed this up to 164 stem, and my computation goes up to about like a 500, more than 500 stem right now. And because I have global basis and I have computer, so I get more results. Okay, now here are some interesting theorem results about these indecomposables. So the first one is the matrix massive product. So May has a theorem saying that all X group can be generated by the matrix massive product by elements in the first line in X1. I mean the first horizontal line of the X group. That so basically you can construct all HIS by all those HIS elements. And I didn't put the definition of this HI prime here. Basically, to get HI prime S, remember that HIS corresponds to a matrix. So you remove the first row of the matrix and you remove the last column of that matrix, then you get this element. So it's kind of smaller to it's smaller than this. And again, you write this in terms of indecomposable, and you can further decompose these elements. This might break into product, but you'll be a product of these elements again. So that you repeat this process, and you can get all these indecomposables that that it looks like this. So on one hand, that gives you an example that May's theorem is true. That indeed you can use these elements in line 1 to generate all indecomposables by matrix massive product. Okay, and actually, by the evidence of the low degree computations, actually there's no indeterminacy. Actually, for low degrees that at least in degrees up to 500. Or in stems up to 500, that there are no other elements in this degree, and so this is either the only indeterminacy that this matrix massive product can have is that 0 might be in it, but it can be proved that 0 is not in it. So actually, you can write equal sign here, but I cannot claim that in general. That because we don't know the whole algebra yet, we don't know if there are other elements in this degree, so it's hard to prove this in general, but I strongly believe that that's an equal sign. Okay, okay, I have to mention that, so actually May actually conjectured this and he has proved this, but it's not in his published work and it's not in his thesis, and it's also, he also couldn't find that proof. So basically he gave me as an assignment. So basically I proved this again, and okay, by the definition of the massive product, this is totally algebraic, so it's possible that you construct this by definition. Okay, now this is the theorem 2. So assume that May's conjecture is true, that these HIS are all the indecomposables. Then in order to move to the next page in the May spectral sequence, it suffices to know the D2 differentials of HIS, and also, of course, also D2 of Bij. But D2 of Bij are already computed by May. In May's thesis, you can find the general formula for D2 of Bij, but we didn't know D2 of HIS in general yet. At least my advisor told me that he has an idea about what this was, but I couldn't find it. But I finished this now already. That it's a theorem that it looks like this. The differential, we can compute the D2 of HIS for all of them. That it looks like this. It's so these are all H in the form of HI, and this is kind of a slightly different from the original HIS. Basically, you increase one of them, and that's it. And there's a restriction. When you increase Hj, it should be still less than the next index, and that's it. And you take this sum of all this kind of increase. Okay. Example: D2 of Hi12 equals H3 Hi13. I mean, you increase 2 by 1, and that's 3. And that 3 agree with that 3. You see that I plus Hj plus 1 agree with that Hj plus 1. Okay, and how to prove it? And I'm using a very straightforward approach. So that I use the Kobar complex for the Steenrod algebra. That I explicitly construct a representing 2 cycle. So by that I mean the differential of that cycle, the leading term of that, the leading filtration of the differential of that cycle, it lives in a filtration that's 2 less than the original filtration. That's what I mean by 2 cycle. So for example, the D2 of Hi1 can be represented by this in the Kobar complex of Ca star. And it sounds kind of scary, but usually these representing cycles would be astronomical. It would be super long. I mean, if you consider the representing cycle of Hi12, there will be roughly kind of 100 semands. It becomes very long very quickly, but later I found out that it's possible to find a cycle for all of them. And if you are curious, it basically is a bit painful, but it's doable. And it's doable. Sorry. So it end up with the a lot of semantics, and these semantics are it's in the bar complex, so it's it's a tensor product of a lot of things, and this amount really depends. And there's the summation also taken over the permutations, because you know that we have the indecomposables correspond to determinants, and so it has something to do with all permutations. But it's a little bit painful to write down the representing cycles, and also to compute, because it's a little bit awkward to deal with the bar complex. It's awkward to write them down. You end up with a long expression, but in the end, the computation is actually not that long. In the end, you can manage to compute the the differential of this cycle. And so the point is that you can write a general cycle for all HIS, and that's how I got to prove I got this formula. And so in history, including like May and Tangora, they all have some, especially Tangora, they all have some tricks to compute these differentials. For example, by relations, and for May, he used like the embedding method, which used the bar complex instead of the bar complex. For bar complex, the arrow, the comparing map between this, between X and the bar complex is going the other way. The arrow goes the other way. So you have to dualize, you embed into the bar complex, and you dualize again. It's again a little bit trouble, and their method does not work for proving this, because their methods are based on the fact that you know the differentials, you know the algebra in low degrees, you know what all elements in those degrees, so you know exactly what indeterminants are, and it turns out that there are no indeterminants. But in order to use their tricks that apply to this low degree, for example, like this one, low degree computations, it does not work for the computation in general, because you have no idea what all possible semantics are. So for May's method, he has to know all the possible semantics that could be on the right hand side, and then you roll them out one by one by computing things in the dual. So it's computing things in the other direction. And but in general, we have no control of the algebra. That at least we haven't proved it yet. We have no idea what possible semantics are here. So it does not work. So, and therefore, I use the bar complex directly, and I construct the representing cycle, and it turns out to be doable. Okay, so if May's conjecture is true, then we can claim that we know the E2 phase of May completely. That we know D2 of Bij, we know D2 of this, and that's it. Okay, so that's the end of my talk. Any questions?
I'll go ahead. Okay, sure, we can do questions first.
Have you calculated any new homotopy groups of spheres, like from all this information?
Yes, that's ongoing. My ongoing project. I actually compute the May spectral sequence. I mean, by up to certain stem, and it's not done yet. So right now, I'm only a little bit further than Tangora's original computation. Actually, Brunner has obtained. Sorry, for May spectral sequence, I cannot compute the homotopy group spheres yet. The May spectral sequence is more focused on the E2 phase of atoms. So my goal is to compute the E2 phase of atoms. For example, I can compute them one by one. I mean, for S, right now we have E2 phase of atoms up to atom filtration like a 5 by some guy in some Taiwanese sorry, I'm forgetting his name, but some people have computed the Adam spectral sequence, the E2 page of Adam spectral sequence, line by line. I mean, S up to 5. I can also do that kind of computation, and so right now the method they are using are kind of either minimal resolution or the lambda algebra. But recently I found that May spectral sequence is still very effective, though people don't quite use it, but still it's a very effective method. And the difficulty is the labor, that there are a lot of tedious computation. I mean, because the May spectral sequence is big, it converges to the Adam spectral sequence. So of course we expect this to be much bigger than that. I mean, by bigger, I mean as a vector space, it's much bigger. So it's hard. It's also harder to use the computer to compute this by brute force. But I recently found that it's very helpful to use the global basis to deal with the May spectral sequence, because though it's much bigger in terms of it's a vector space, but there are less relations compared to the Adam spectral sequence. For example, the E1 page of May, which is the polynomial algebra. We know the polynomial algebra is huge in size, but the number of relations is 0. So if there are less relations, then the global basis is a very useful tool to handle that. So right now I've implemented some program using global basis, and I'm using it to do this certain kind of symbolic computation. I can compute like what the algebra are. They are all described by global basis. I mean, in terms of generators and the generating relations.
Thanks.
I have another question. So when I read the paper by May, he computes the second page, basically saying that if I remember correctly, what the associated gradient for stringent algebra is something like a universal development algebra for restricted Lie algebra. And this is tell you what you can compute your X groups by using something like a Chevalier complex. So my question is, can you restate your conjectures in this generality?
Oh, yeah, I'm actually curious of that. Actually, for example, for odd prime, this
For odd prime, there's some subtleties.
Yeah, for odd prime, the story are very different because it's no longer a polynomial algebra. So let's skip that. But for prime 2 and other context, yeah, I'm curious about that too. I believe that there are, I haven't studied those yet, but I believe that there are certain
no, because for example, let's show conjecture 1. It's pretty long, and it's I do not understand how to use it without a computer, which like for me is like it's very sad. So possibly like in bigger generality, you could say it more compactly. You can package this information more compactly. Do you think about it?
Yeah, I think for some hard spectral sequence, and if you consider the May type of, if you use the May spectral sequence again and compute the May spectral sequence of that, at least I believe that those E2 pairs of May are understandable. At least there's a hope that you can list all relations. But I think for E2 pairs of atoms, or for example for E4 page of May, I don't believe there's a, maybe theoretically it's possible, but I don't believe human can manage to describe the algebra at all.
I simply want to split the problem on two. First, you compute the corresponding Lie algebra, restricted Lie algebra, and after that, if you computed this one, you will be able to compute with homology of this Chevalier complex.
So I still don't get your question.
Sorry. Yeah. I think that it's probably possible to split the problem on two. First, you compute, you're saying something about your restricted Lie algebra, which probably also not very simple. But if you know this information, you will be able to describe all your indecomposable elements for homologies of corresponding Chevalier complex. And also, it will be very interesting if you're able to say in conjecture 2 when homology is a nilpotent free in terms of a corresponding Lie algebra.
Yeah, I'll be
I think it's
interesting.
Really
I also believe that it's also true elsewhere, but I haven't studied in other contexts yet. But it would be interesting to study what
because
it
question
looks like in other contexts.
Completely algebraic, and not about only one object. It's about like actually important object in algebra.
Yes.
This was my point. Okay.
I'm interested in that. Yeah.
Any other questions for Weinan? Okay, I'll go ahead and unmute everyone. And